Hello, everyone. So we finished up last time on gases and gas loss. The next chapter we're moving into is chapter 11, which is on intermolecular forces. So in order to get into that, let's just do a quick review of the different states of matter. So we've got gases, liquids, and solids. And if you all remember, gases, which have these really unique properties, allow them to be highly compressible. They can change their volume, so they assume the shape of whatever container they're in. And the molecules are super far apart, so they have such a low density that the particles, very, very rarely interact with each other. And because of these qualities of a gas, they can follow the gas laws. Now, liquids and solids differ from gases in that they are incompressible, so they have a fixed volume. Liquids are molecules that are closer together than gases, but they don't have a rigid arrangement. So liquids have this fluid quality to them, or molecules can move or roll past each other. Solids also have that incompressible quality, but these things are even more rigid than our liquids, and that the molecules are really packed together and they're all sort of aligned like soldiers in an army. So solids and liquids are known as condensed phases just because they're closer together. So these intermolecular forces that we're going to talk about are going to really apply to liquids and solids. They don't apply so much to gases, really because of this thing right here. The molecules are so far apart that we assume the molecules aren't interacting. On a liquid and a solid scale, molecules do actually interact with each other. So before we get into the intermolecular forces, let's go back to our primary bonding forces. So these are what sort of freeze a material into its solid crystalline shape. And these are all very strong, okay? The strongest of the strong. So if you have ionic bonding, metallic bonding, or covalent bonding, and when I say covalent bonding, I specifically mean covalent network, and we'll talk about that in a second. These are going to be much stronger than any of your intermolecular forces, or what we call van der Waals forces. So ionic bonding is, hopefully just what you remember. It's a metal and a non-metal, or it's a metal combined with a polyatomic ion, or this sort of attraction between our positively charged and our negatively charged ions. So some examples of ionic structures or ionic formulas would be CaO, calcium hydroxide, NaF. Or let's throw something in with a polyatomic ion, MgOH2. So we've got a metal combined with something that's behaving as a negatively charged anion. Super, super, super strong ionic bonding. If I was to draw this out, and I'm actually going to do it on the other sheet. So I got to ditch these notes here. So if I was to draw, say, NaCl, These aren't molecules, so not a molecule. Or we don't have like an Na and a Cl buddied together, and then here's another Na and a Cl buddied together, and they're just sort of floating around. That is not what's happening in ionic. Instead, what we have is a lattice structure or a three-dimensional interlocking structure, so lattice. So I'm going to have an Na plus and a Cl minus, and an Na plus and a Cl minus, Na plus, Cl minus, and this will continue till you hit the edge of your material. And it's not just side to side, it's also up and down. So above an Na plus, there will be a Cl minus, and below it will be a Cl minus. Here there'll be an Na plus, an Na plus, and actually then moving back into the page or forward and out, there's also this interlocking structure. So this is particularly stable and strong. So it's hard to come in here and like cut this up. You can do it, you know, manually with a knife or something. It'd be pretty hard to cut a salt cube with a knife, but if you had a really, really sharp knife moving very quickly, you might be able to saw through this. If we were to try and melt this, it would take a lot of energy to break these things up and move it into a liquid or a gaseous form. And so this is all happening between cations and anions. Back over to our notes here, and let me draw. So we said what? CaO, NaF, MgOH2. All examples of this interlocking structure. The next thing is metallic bonding. So metallic bonding is going to happen between metal atoms. So there's not going to be any sort of non-metal counterpart like we have in ionic. Instead, we're going to have all silver or all iron, you know, or all magnesium. And what we have happening here is a web of metal atoms and electrons. And what's actually kind of cool about metallic bonding is those electrons are free to move through the structure. So they're not just free to kind of oscillate back and forth between adjacent atoms. They actually can move or kind of meld their way through the structure, which is what allows metals to conduct electricity. So if I was to draw a structure for this, for our metallic bonding, so here we've got ionic, metallic, let's just go with, what do we want to do? Do silver. So we've got silver, Ag, and we've kind of got our electron cloud around it. And then I've got these electrons, and I'm actually going to put them sort of in between the silvers, because the electrons, I don't even want to say they're being shared. They're just sort of free to float through this structure. And so this electron could end up, you know, all the way down here. This is also a very strong structure. And all of these are strong structures, but this is strong. Think about what the melting points are of silver, right, or gold. You've got to pump a good amount of energy in there to phase change that. The last one we have is covalent bonding. And when I'm talking about covalent bonding, I really mean like a covalent three-dimensional structure. So an example of what I'm talking about here would be diamond. So in this, we have a 3D web of covalent bonds where everything is covalently bonded to everything else. So what I am not talking about here is just a molecule that has covalent bonds. So I'm talking about something like, okay, we said diamond. So we've got carbon bonded to carbon, bonded to carbon, and there are carbons actually coming off of this thing in all directions. And this has a carbon, and we could just sort of continue it on. As opposed to versus, so it's this, not this, which would be, let's say, methane, carbon attached to a hydrogen, attached to a hydrogen, attached to a hydrogen, attached to a hydrogen. And this is sort of an isolated molecule, right? We're looking more at a structure where we have covalent bonds throughout. So I'm actually pulled up an image because this is kind of hard to see, but the structure of diamond looks something like this. So we've got carbon atoms, and they form these tetrahedrals where each carbon is connected to another carbon over and over and over again. This is super strong, very, very, very strong. Other examples of this would be like silicate minerals or silicon dioxide, sand, also very, very strong. So what tends to be the things that will form this interconnected covalent bonding are going to be materials. So materials that contain only silicon, really, and oxygen, or I'm sorry, silicon and carbon. Silicon and carbon. Sometimes they have other things stuck in them. So like a SiO2, which is silicon dioxide, very strong material. But we get this three-dimensional webbing of silicon to silicon or carbon to carbon. So if we ever want to order things as far as strength, these are always going to be strong or much stronger than your intermolecular forces. Okay? They will always win out. So if I say, hey, I've got hydrogen bonding and I've got an ionic bond, which one's stronger? Ionic bond, one of these guys will always win out over one of these guys. So moving on to intermolecular forces, hopefully this stuff up here isn't really anything new for y'all, but intermolecular forces are exactly what they sound like. And this is, sometimes you'll hear them called van der Waals forces, but this is the force or the attraction between adjacent molecules, okay? So how is this different than what we have up here? Well, up on the top, we're dealing with a three-dimensional, either a lattice structure or a covalent structure or this metallic where everything is, sort of bonded or attached to everything else. These intermolecular forces are going to look more at isolated molecules that somehow kind of stick or attract each other. So if I had something like, for instance, H2O, that in and of itself is like an isolated little molecule, right, or packet. And I've got another H2O over here and another H2O over here. Because of a couple different forces, these things are going to sort of attract each other, right? That's why water has this sort of sticky quality to it. It makes like little droplets as opposed to just breaking down into single atoms. So let's look at a couple of the different intermolecular forces. There's three that you all want to know. We have London dispersion forces, a dipole-dipole, which may sound familiar, and you're probably will already know about that from the bonding theories. And then we have this thing called hydrogen bonding. So London dispersion forces we find in all molecular solids and liquids. So anything that isn't ionic, metallic, or covalent is going to have a London dispersion force. So it's very common. It is the weakest of all of them. Weakest, let's say, found in all. So why we get these London dispersion forces is we get what's known as a temporary dipole moment. Temporary dipole moment. And because the dipole moment is temporary, a London dispersion force is also temporary. So it'll happen really, really quickly, and then it'll kind of dissipate, and another adjacent molecule will have a London dispersion, and then it'll dissipate, and so on and so on. So let's look at helium atoms and how we can see London dispersion in helium atoms. Because in general, helium atoms, if we had two helium atoms next to each other, I mean, think about what helium is. Helium is a noble gas. In general, we don't really expect it to react with anything. But there is still a small amount of stickiness to helium to itself, especially if we get it into that liquid and solid form. So helium consists of two protons in the center. And then around it, we have two electrons, right? And these electrons in general want to get as far away from each other as possible. So usually it's in this really balanced ordered structure, but that isn't always the case. Sometimes what will happen is these electrons will get like knocked off or moved over to one side. So this electron over here, let's ditch him and let's actually put him somewhere over here. And then let's ditch this electron and kind of put him over here as well. We jostled it somehow, or there was some sort of energetic current that ran through this that moved the electrons to one side. So what this is doing is creating what's known as a temporary dipole or an asymmetry in charge. We're going to get an overall positive charge here, right? And you've got this little symbol that kind of looks like an infinity symbol with a plus. And then on this side over here, we're getting a negative charge. Right now, at some point, these electrons will oscillate back into a more stable place for them. But while this is happening, it sort of creates a chain reaction to adjacent hydrogens, or rather helium. So if I have another helium over here that has two protons, and it has its, little electron cloud. Well, if there's a lot of negativity happening from these electrons, the electrons in this guy are going to try and move away from there. So they're going to kind of move to this side as well. Maybe not as dramatically as they were here. And again, this will form sort of a temporary dipole. So we get a positive and we get a negative, and then those sort of temporarily stick together. What happens with this guy? He will sort of pass that on to the next helium. And let's say it's even less dramatic. So maybe the electrons are almost back to their normal state. So we have a temporary positive on one side and a temporary negative on the other. Now, in order for this, and again, we'll see this sort of dissipate as we move out, and this is temporary. So at some point, these guys are going to come back to a more electronically stable situation, and it'll sort of fade or dissipate. So we see this happen in all of our molecular structures. So if I ask you, hey, does this molecular structure have, London dispersion forces? You could always say yes, most common. So down here, we have between instantaneous dipoles or induced dipoles. So we've created, or we haven't, but the molecules have created an instantaneous asymmetry in their charge, and they kind of stick together. You can induce this as well in a lab. You can create a dipole in certain materials. This happens between all molecules, so it doesn't matter if the material is polar or non-polar. They will create a London dispersion. And then kind of I think we have it already up at the top, but we can reiterate this is the weakest of the intermolecular forces. So what if we had something like O2 versus N2? So both of these are nonpolar. If you drew out their Lewis dot structures, they would be very balanced. They're sharing the electrons equally. So there's no permanent dipole moment in these things. They're nice and balanced. So which one of these would we expect to have a higher London dispersion force? Because they both have London dispersion forces, but which one would have a greater one? Well, it has to do with this idea of polarizability. And polarizability is how easy an atom's electron cloud can be distributed or disturbed. So how easily an atom's electrons can be disturbed. Or how easy is it to jostle them? Now, the more electrons you have, all right, the more ease you have, the easier it is to jostle, easier to disturb. How do we get more electrons? Well, we need to have more material. How do we get more material? Well, we need to have a higher molar mass, okay? So if we have a high molar mass, that is going to lead us to a higher number of electrons. So higher electrons number. This will increase our polarizability. So increase polarizability, which at the end will increase our London dispersion force, or our LDFs. So going back to these two over here, if I wanted to know which one had a stronger London dispersion force or which one was sort of stickier to itself, I would have to look at the molar masses. So oxygen, in its diatomic form, O2 has a molar mass of, come on, 32 grams per mole. Nitrogen, in its diatomic, has a molar mass of only 28 grams per mole. So the oxygen is bigger. Higher molar mass means more electrons, means it's easier to jostle it. Higher polarizability, which means we have stronger London dispersion forces. So in this instance, I would say O2 wins out on that one. How about, I'll give you another one. Let's say we're comparing, CH4 versus CF4. And I want you to tell me which one has a greater London dispersion force. Okay, so looking at this, and I'm not even actually going to calculate the molar masses, but we've got carbon mixed with hydrogen and carbon, and they're both 4. So carbon and 4 hydrogens and carbon and 4 fluorines. Well, hydrogen has a mass of 1. Okay, fluorine has a mass of 19. This thing is going to have a lot more electrons. It's going to be a lot easier to disperse that, the electron cloud. So we would expect to see more temporary dipole moments where the CF4s are able to kind of stick or clump to themselves.
So there's not necessarily like a trend for this on the table other than it's related to the molar mass.
It's just related to the molar mass. So if you were to have 2 things, just add their molar masses up and figure out which one's heavier. Okay, that covers one of these factors. When talking about our London dispersion force, there is another thing that affects our LDFs as well, and that is the shape of the molecule. So long, skinny molecules will tend to have stronger forces because they have an increase in surface area. Or, when they're more compact, they're kind of more globular, they'll stay to themselves. When they're long and skinny, they can kind of intertwine or wrap around each other. And I'll give you an example for this. If we have, 2, 3, 4, 5, we got pentane. And I don't expect you all to know the structure for pentane, but if I was to, give you each of the structures, you would be able to tell me which one has a stronger London dispersion force. So pentane can be written in a couple different ways, pent meaning 5, ane meaning they're all single bonded. So one way is to have carbon in the center and then CH3, 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 CH3. So I've got 5 carbons. So the formula for this is C5 and then H12. There is another way that I can actually draw this. I could draw it as a single chain, CH3, CH2, CH2, 2, 1, 2, 3, 4, CH3. Now, again, I wouldn't expect you to know this because this is more organic stuff, but just looking at the different shapes, they have the same formula, so they have the same molar mass, but this guy is in more of a compact globular shape. This guy is in a longer, skinnier shape. So this one is going to have a larger London dispersion force. Okay. Easier for this to kind of align with other molecules, CH3, CH2, 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 CH3. Look at all these places where we can create these temporary dipoles and have it stick to itself. So the next type of intermolecular force is a dipole-dipole force. So these are for polar molecules. Important thing, it's between two molecules that have a permanent dipole. Permanent meaning that the dipole isn't temporary, it's not going to go away. So let's draw out a couple things that are polar. Anything that has a lone pair of electrons on the central atom is going to be polar. So great example.
Can you repeat that again?
Yeah, one thing, anything that has lone pair of electrons on the central atom will be polar. So remember, lone polar pair. So pH3, if I was to draw out its Lewis dot structure, we have 8 electrons. I put the P in the center, H, 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 bond it together, and then I have 2 lone pairs of electrons right here. This is giving it a quality of being polar. This side will have an overall, over on this side, this will have a negative charge, and this will have sort of a positive charge around the hydrogens. That's permanent though. That's not something that comes and goes. Another example of a polar material would be CH3F. In this structure, I've got carbon bonded to 3 hydrogens and 1 fluorine. Okay. And this would have some electrons around him. This is not balanced. Now, I know there aren't any lone pairs on the central atoms. So there is a tug of war going in all balanced 4 directions, like that tetrahedral shape, but look at what is happening here. These are sort of wimpy polars. This guy is a very strong pole. So this is also creating an asymmetry. So we would expect to find sort of a negative charge on the fluorines portion, and then along the hydrogens, we would expect to see a little bit of a positive charge. And again, that's not something that comes and goes. That's a permanent dipole. And so if we've got this negative charge over here and these positive charges here, well, what happens when I bump another one of these molecules up against it? Because liquids and solids are close to each other, right? So these can interact with each other. It's not like a gas where these things are so far away, they can't interact. They're gonna play around. They're gonna mess around with each other. So this hydrogen that has a positive dipole moment is gonna stick to the fluorine that has a negative dipole moment. Water also does this, but water has a special dipole moment that we'll talk about in a second. So if you see lone pairs, or if you see that you don't have the same atoms around the central atom and your tug of war is not an even playing field, then you know that you're polar. So we really will only take into account this dipole moment when the molecules are close together. So that means that this is applying to liquid and solid form or solid phase. If we vaporize something or if we turn it into a gas, this dipole-dipole moment doesn't really have any sort of effect. Going back here, let's say I had 2 of these, but I have vaporized this material. It's in gaseous form. These guys will be so far away from each other and they'll be moving so fast that any little attraction they could have is sort of negligible. So they'll just keep moving in their own direction. So one thing that we've got here is the more polar the molecule, the greater the force. So if we have an asymmetry, let's say we're doing, sorry, my pen is not working. Come on. Okay, so let's say we have put together HBr and HCl. Okay, both of these are creating a dipole-dipole moment. The hydrogen is going to give us an overall plus charge. In this case, the bromine is going to give us the negative because the electrons are going to want to sit closer to bromine. As far as this one is concerned, again, we've got a positive by the hydrogen, and we're going to have sort of a negative dipole by the chlorine. But which one creates a stronger dipole-dipole moment has to do with how polar the molecule is. So which one has a polar bond here, both of them, but which one has a stronger polar bond? This guy here has a stronger polar bond. How do I calculate that or find that? Remember your electronegativities. So chlorine has a higher electronegativity than bromine, so the difference between those two is greater. Bromine's lower down. Remember, the highest electronegativity is going to be fluorine in that upper right-hand corner. So do note, though, that any of these structures that have a dipole-dipole moment also have London dispersion forces. So this thing here, those have dipoles and they have London dispersion. So you want to layer both of those on top. So we get LDFs, London dispersion forces, and we're also getting our dipole. Now, the third type of bonding that we have intermolecular force that we have is hydrogen bonding. And this is sort of a special type of dipole. So you can think of it as a dipole moment, but it happens when you have hydrogen bonded to N, O, or F. So if you want on your periodic chart, you can sort of highlight N, O, or F. If you ever see hydrogen in combination with those, you're dealing with hydrogen bonding. So an example would be HF, hydrogen bonded to fluorine. This is also CH3OH. If you ever see OH written like this, you can assume that the oxygen and the hydrogen are bonded together. That will give you hydrogen bonds, so yes. Let me draw this one out for you just so you can get a sort of visual of it. So CH3OH, again, anytime you see OH written out like that, clump it together. Here we have carbon bonded to a hydrogen, a hydrogen, a hydrogen, and then it's bonded to an oxygen that's bonded to a hydrogen. This right here is what makes it a hydrogen, or gives it the hydrogen bonding quality. Hydrogen bonding is stronger than dipole-dipole. Okay, so if you have hydrogen bonding, you will actually have sort of a stickier quality. Things that have those HNs, HOs, or HFs will be easier to clump together. It's going to be harder to melt them and vaporize them. I want to show you one that isn't hydrogen bonding. So we had talked about it earlier, CH3F, CH3F. This is not, so let's go with a big NO here. Yes, it does have hydrogen and it does have fluorine, but let's attach them together. Carbon goes in the center, hydrogen goes on the sides, and then fluorine also goes on the side. If you notice here, the hydrogen isn't directly bonded to the fluorine. If they aren't connected to each other, we don't consider that a hydrogen bond. So this thing here would be, it does have a dipole moment, so it would be dipole-dipole forces. It just isn't strong enough to be classified as a hydrogen bond. Water, H2O, that's a great example of hydrogen bonding. So I've got hydrogen bonded to oxygen, bonded to hydrogen, and we've got these lone pairs. This connection here is what makes it a hydrogen bond. So if I have another water over here, the hydrogen end is going to stick to the oxygen end, and it's going to give it this really tacky quality. Why are hydrogen bonds extra special? Right? Why do they get their own grouping? Because they're stronger. And they're stronger because they have a higher electronegativity difference. So the difference between H and F is substantially greater than the difference between H and Cl or H and Br, right? Higher numbers, that fluorine, oxygen, nitrogen right along the top there have a really big electronegativity. Gives us, or these properties, the dipole-dipole, the hydrogen bonding, explains why ice floats. Because the way that water will attach to itself and structure, it's actually less dense in its solid form than in its liquid form. Also lets us, has helped us to figure out the structure of DNA, the protein structure of DNA. The reason it coils in on itself, or you get that double helix, is because you have hydrogen bonding. So the material or the DNA is able to stick to itself in that structure. So if we were to order all of these things together, the strength of forces are going to go like this. So strongest is going to be the covalent bond. And when I say covalent bond, I don't mean this here. I mean that three-dimensional covalent net or covalent lattice. Then we have our metallic bonding. So metallic bonding is going to actually be a little bit stronger than our ionic bonding. And then after we get through our primary bonds, then we go into our intermolecular forces. Hydrogen bonding is the strongest of the intermolecular force, then dipole-dipole, and then London dispersion. So I want you to go ahead and looking at this here, HF, N2, O2, and HCl, I want you to put those in order of strength. So put them from weakest to strongest. Okay, so looking at this first one here, weakest to strongest. So I'm going to find the strongest thing. The strongest thing is going to be our covalent. Sorry, there we go. Okay, our covalent bond. So are any of these in a covalent three-dimensional structure? It needs to contain carbon or silicon. It's really going to be diamond or SiO2. I don't see any of those as an option, so we're not going to put that. Metallic bonding, I don't have any metals by themselves here. Ionic bonding, I don't have any salts. So all of these are examples of intermolecular forces. So it's going to be one of these. So strongest one is going to be a hydrogen bond. That's going to be hydrogen combined with fluorine, oxygen, or nitrogen. That first guy there, HF. So I'm going to put him over here, H. Well, why don't I put it in the same order that they have it here? So we'll put HF first. We'll go strongest to weakest, just so it's not confusing. So strongest and then weakest. So our strongest here is going to be HF. Then after that, I'm looking to see if I have any more hydrogen bonds, and I don't. So I'm going to move into dipole. Dipole moments are any of these polar molecules. Yeah, this guy right here is a polar molecule. So HCl comes next. After that, I need to take a peek at my London dispersion. Both nitrogen and oxygen are London dispersions. They don't have, they only have temporary dipoles. They don't have anything permanent. So we're going to have to go off of size. The bigger the molecule, the stronger the London dispersion. So O2 is larger. We're going to put that. And then nitrogen is the tiniest and the weakest. So HF is greater than HCl, is greater than O2, is greater than the really weak forces of two adjacent N2s. Looking here at this second one, that if we go in order of strength, again, I don't have any covalent metallic or ionic bonding, so I leave those out. I do have hydrogen bonding. So that last guy, the CH3OH, that is a hydrogen bond. So I'm going to put that guy there. The first one, CH3OH. This is what makes it hydrogen. The next thing that we have, I've got a polar molecule and a non-polar molecule. This, again, the fluorine and the hydrogens aren't attached to each other, so we don't consider that hydrogen bonding. But this is a polar molecule, so it creates a dipole-dipole moment. So we'll go CF3H. And then the last thing is this CF4, which is nonpolar, very balanced. The only way it's going to stick to itself is if there's a temporary dipole. So why do we care about these intermolecular forces? Because they have a big effect on phase changes or the physical properties of the material. Hello. So as far as melting and boiling points are concerned, the greater your intermolecular force is, so if you have a large intermolecular force, what do you think is going to happen? Well, if the material is stuck to itself really well, it's going to be hard to break its solid form and put it in liquid form. Or if I'm a liquid and I have a high intermolecular force, it's going to be hard to break me up into a gas. So the higher the intermolecular force is, the higher your melting point and boiling point will be. You need more energy to break up two things that like each other than two things that don't like each other or don't have that sort of self-stickiness. The next quality is vapor pressure. Vapor pressure is the pressure that's exerted by molecules at the surface of a liquid. So put a little drawing over here. If I've got a container of, just say it's water. There's an atmospheric pressure that's pushing down. But there's also a vapor pressure or a pressure from the liquid that's pushing back up against the gas that sits above it. We talked about in gases last time that idea of water vapor pressure, or this liquid water that we're collecting the gas over, applying a pressure to the surrounding collected gas. So if we have a high IMF or high intermolecular force, that means that the water or the material that's in here, let's say it's water, it means that it likes itself. So it's sticking to itself. It's kind of clumping together. So a high IMF is actually going to lead to a lower vapor pressure. And vice versa, a low IMF, a low intermolecular force, will create a high vapor pressure. So if I've got a material that isn't very stuck to itself, the molecules are sort of just, they're in the same space, but they don't really have any sort of connection to each other, they're going to expand or apply a lot of pressure to the surrounding gas. We have another term here called volatility, and that's how easy a liquid evaporates. So like gasoline, for instance, is very volatile. It means that it can turn into a gas really easily. I'm sure you've had this happen where you've spilled some liquid gasoline on your hands at the gas pump and then it like fills the entire car with that odor. It's because it's jumping from its liquid to its gas form very easily. How do these two relate to each other? Well, if I have a low IMF, if I have low intermolecular forces, my two adjacent molecules aren't sticky, we would expect that there would be a high volatility. And it's easy for the molecules to pull away from each other and evaporate. So it evaporates readily. Viscosity, when something is viscous, this means that it has it's classifying its resistance to flow. So if I say something has a high viscosity, it means it's really thick, like syrup has a really high viscosity. It's resisting the ability to flow. Something with a low viscosity would be, well, less viscosity would be like water. It's easier for that to flow. So if we have a high intermolecular force, that means that adjacent molecules are sticking to each other, we would expect to have a high viscosity. Right? And vice versa, if we have a low intermolecular force, if adjacent atoms or adjacent molecules rather aren't interested in each other, it's much easier for them to move and flow past each other. Surface tension is the ability for a liquid to create sort of a surface or a semi-solid quality to it. So water has a surface tension. That's why it's not a strong enough surface tension for us to walk on. But there are certain types of bugs that have really wide surface area for their little foot pads, and they can actually walk on water because there's a certain amount of surface tension. So if we have an increased IMF or intermolecular force, we would expect that we would have an increase in our surface tension. Right? The stickier the material is to itself, the more connected the adjacent molecules are, the more it's going to behave in that sort of solid-like form. Hopefully these phase changes are nothing surprising. We've got something called sublimation. That's when we're going from a solid to a gas. Vaporization is when we're going from a liquid to a gas. And then melting or fusion is when we're going from a solid to a liquid. How do I get through, or how do I make all of these things happen? One way is to somehow release heat or give heat up. So all of these are endothermic. Or we would expect to have a delta H that's positive. So if I want to go from a solid to a gas, I am going to need to pump energy into the system, right? The solid needs to absorb energy in order to become like a gas. Deposition is going from a gas to a solid, so it's the inverse of sublimation. Condensation is gas to liquid, and then freezing is liquid to solid. So hopefully you can kind of see how these are the opposite of each other. If this is endothermic over here, these are all exothermic. They're going to produce heat, or we're going to have a negative delta H. So freezing, when we're going from a liquid to a solid, you can actually experience this firsthand when you when you're outside and it starts snowing. When we get that snow, what's happening is we're freezing the liquid in the clouds. This releases heat and it will actually feel a little bit warmer. So anytime we go through a phase change, we have to either add energy or we have to remove energy. If we're trying to move up in our phases from solid all the way up to gas, we have to put energy into the system. If we're going from a gas and dropping down in our phases towards a solid, we are going to need to release energy to create those bonds. So at any of these phases or phase changes, we are actually going to release or absorb a very specific amount of energy. So the heat of fusion, and there's a bunch of these, but the heat of fusion is the energy required to melt a solid at its melting point. So right here. But also, this number also applies here. We just have to flip the sign. So the heat of fusion, or the amount of energy that is needed to take a mole of the material in, say, kilojoules. So we've got ethanol down here. Ethanol has a heat of fusion of 5.02 kilojoules for every 1 mole. So if I had 1 mole of ethanol, it would take 5.02 kilojoules. The opposite of is true for the heat of, the opposite of this is true for freezing. So if I wanted to, instead of going from solid to liquid, go from liquid back to solid, I would take whatever my heat of fusion is and I would just put a negative value in front of it. We also have heat of vaporization. Heat of vaporization is talking about liquid to gas, or we can take the opposite sign of it and go from a gas to a liquid. In general, your heat of vaporization, and you'll see it as this delta H of VAP in kilojoules per mole. In general, your heat of vaporization is much greater than your heat of fusion. So it takes way more energy to go from liquid to gas than it does to go from solid to liquid. Think about what's happening when we're going from solid to liquid. We're just breaking up the lattice structure of the material or the adjacent molecules, but we're not pulling them away from each other. So they're still allowed to interact with each other. When we're going from a liquid to a gas, we're literally pulling these molecules very, very far away from each other so that they can no longer interact with each other. So lots of energy there. So let's look at these 2 values with ethanol. The enthalpy of fusion, so enthalpy of fusion is talking about my solid to liquid of ethanol is 5.02 kilojoules a mole, and its enthalpy of vaporization is 38.56 kilojoules per mole. If you're wondering where these numbers come from, they're in an appendix in your textbook, so I would not expect you to have these memorized. All right. How much energy does it require to melt 55.0 grams of ethanol? So in this problem, we have to decide what is it wanting us to do. Here, this first part, part one, is asking to melt, right? So how much energy does it require to melt? So if we're melting, we're going to be using heat of fusion. So I want to use this number for my first part, this 5.02 kilojoules per mole. What are we given? We're given an amount of ethanol, but are we given it in moles? We're not. It's not too difficult. So 55.0 grams of ethanol. Oh, yeah, and I wouldn't expect you to know the formula for ethanol. So let me give that to you. So ethanol is going to be C2H5OH. So if we're in grams of ethanol, C2H5OH, and we want to convert it into moles, well, 1 mole of C2H5OH is equivalent to 46.08 grams. So grams will cancel, and now we're in moles of our material. Well, all I have to do is take that and multiply it by this heat of fusion, because look at the heat of fusion has 2 units. It has kilojoules and it has mole. So just adding that on there, 5.02 kilojoules are going to be needed for every 1 mole of my ethanol, C2H3OH. Moles will disappear and we'll be left with units of just kilojoules. In this case, it is 5.99 kilojoules. I want you to do the same thing, but I want you to tell me what the energy is for to vaporize the material. Okay, so we have 55.0 grams of ethanol, but we're going to now take it from liquid and put it into gaseous form. Okay, so this one isn't really much of a stretch from what we did on the first one. The only difference is that we're not going to use heat of fusion. We'll use heat or enthalpy of vaporization. So if I have 55 grams of the ethanol, okay, I can use the same value, 1 mole for every 46.8 grams. The last step is where it's going to be different. So instead of the 5.02 kilojoules per mole, we actually have to use this bigger number of 38.56 kilojoules in every 1 mole. So much larger, right? 6 times or so as large. So our ending number, when we plug that in, is 46 kilojoules.
Where is that 38.56 coming from?
It is coming from within the problem itself. Sorry, I'm trying to, there we go. So it says the enthalpy of fusion is 5.02 and the enthalpy of vaporization is 38.56 kilojoules per mole. So again, that information would have to be given to you. It's a set value for every material. So the heat of vaporization for water is going to be different than that of ethanol, but it is consistent for an entire sample, whether you're running this, here, you're running it in Europe, you'll use the same vaporization value. So this enthalpy of fusion and enthalpy of vaporization leads us into what we have here, which is known as a heating curve. So this is when I have a material and I'm just adding heat. I'm not adjusting pressure or amount or anything like that. I'm just going to apply heat to the material. And what I would expect is that, let's say this is a heating curve for water. So we start with ice. I'm going to heat the ice up until I reach its melting point, which is at 0 degrees if we're at 1 ATM. And then when I go along through the process of melting, in this period right here where we're at 0 degrees, this is known as a phase change, right? We're going from solid to liquid. There is no temperature change during a phase change. Okay? So we can have temperature change within a phase. So I can actually heat the ice itself up. Ice can have a -25, a -23, to a 0. This is where we use Q equals MCAT. All right, so any of the angles are the Q equal MCAT stuff, which you guys already know, where we have that temperature change. The flat parts where we have these phase changes, this is where you're going to use your heat of fusion and your heat of vaporization. So back to the ice, I heated it up along this melting point. I'm not changing temperature. I'm using all of the energy that's being added to phase change. Then at a certain point, I go from having some ice to being only a liquid. Once I'm completely a liquid, then I can start to change the temperature of the liquid. Think about all the different temperatures you can have for water, right? You can have water in a cup that is got ice that's almost close to 0 degrees. And then you can have water in a teacup that's almost 100 degrees Celsius. So how do we change here? Again, this is going to happen using Q equals MCAT. Once we get to our boiling point, we will have liquid and gas simultaneously until we've converted all of the material to gas. Then when we've reached our gaseous point, we can actually increase the temperature again. So when looking at these heating curves, we're going to be breaking them apart into phase changes where it's flat, temperature changes where it's angled, and then we add them all together. So here's a practice problem for that. So it says how much energy is required to convert, we've got 55 grams of ice, and the ice is at -6.0 degrees Celsius, to liquid at 55.0, and I'm assuming that's supposed to be degrees Celsius. So when I'm working on these, I always like to draw a curve for it. So the first thing I'm doing is starting as ice. And am I at my 0 degree point for ice? No, I'm actually below it. So I'm starting at -6.0 degrees Celsius. So if I want to melt my ice, the first thing I need to do is increase its temperature to the melting temperature. So what is the melting temperature of ice? 0 degrees Celsius. So I need to change it from -6 all the way up to 0 degrees Celsius. Then from there, I can melt it, right? So we're a liquid, or what rather, we're a solid here. We want to get this thing into liquid form. So I need to pump a bunch of energy in it to phase change. Remember, the flats are when we're going from one phase to another. In this case, we're going from solid to liquid. Now, does it want the material as a liquid at 0 degrees Celsius? No, it wants it at 55 degrees Celsius. So I need to take this and then take my liquid and increase its temperature all the way up to 55 degrees Celsius. Here we're dealing with a liquid. So you can think of this as a 3-step problem. The first step, 1, is raising the temperature of the solid ice. The second step, 2, is transitioning from a solid to a liquid. And the third step is taking my liquid and raising it from a temperature of 0 degrees to 55 degrees. On the flats, you want to use vaporization, you want to use fusions. On the angles, you want to use Q equals MCAT. So for the first one, section 1, I have ice at -6. It's starting at -6, and I want to bring it up to 0 degrees. So how much energy does that require? Q equals MC delta T. So M is my mass. Well, how much water do I have? 55.0 grams. C is the specific heat of water. Does anyone remember what the specific heat of water is? 4.184 joules per gram degree Celsius. And then my change in temperature is final minus initial. So 0 minus a -6, or 6 degrees Celsius, 6.0 degrees Celsius. So when I plug that in, grams will cancel, Celsius will cancel, and I'll be left with units of just joules, which is perfect. And we get 6.8, or rather, I'm sorry, 600, a little bigger than that. 689.7 joules. So this is just step 1. Then I need to figure out step 2. Step 2 is a phase change from solid to liquid. So I need to know what my heat of fusion is for water. Well, it gives it to us right here. It says the heat of fusion is 6.01 kilojoules per mole. Oh, I told you guys, I'm so sorry. Oh no. Scratch this one part right here. So we are in the solid range, my bad. We're in the solid range from here to here. We don't want to be using 4.184 because that is for liquid water. We actually want to be using the 2.09. 2.09 joules per gram degree Celsius. So sorry. So yeah, if you're in the solid, you need to use the specific heat for the solid. If you're in the liquid, you need to use the specific heat for the liquid. If you're in the gas, the specific heat for the gas. The answer is still the same. I just plugged the wrong number in. Sorry about that. So there's our heat of fusion. We have 55 grams of ice, so 55.0 grams of H2O. I need to convert that into moles. So every 1 mole of H2O is equivalent to roughly 18 grams of H2O. And then I know that for every 1 mole of H2O, I get 6.01 kilojoules per mole. Cancels. And then we just plug that into our calculator, and it is 18.3 kilojoules. I got 1 more minute here. The last step is 3. I have to take my liquid water and go from 0 to 55. So Q equals MCAT again. So we'll take the 55 grams of water. Now we multiply it by the 4.184. And then our change in temperature is 55 minus 0, or 55 degrees Celsius. When I put this into my calculator, I get, oops, 30, sorry, 1,200, 1,200 or 12,644.5 joules. Okay. Units will all cancel. You'll just be left with the unit of joule. So you have found the values for each step. The last thing you need to do is take 1 plus 2 plus 3, the values for each of those, or your total is going to equal your 689.7 joules plus your 18.3 kilojoules plus your 12,644.5 joules. Now, obviously the units all need to be the same, so make sure that you convert them all into joules, or I'd convert them all into kilojoules. Kilojoules tends to be a more useful value. And then you get your final answer. So let's move this over. 1, 2, 3. 1, 2, 3. We end up with, adding all those up, I get 31.6 kilojoules. Okay, so it takes 31.6 kilojoules to go through this stair step. I highly recommend creating one of these before you start to attack all this, because it just gives you a sort of an organization for the information. Okay, so we'll stop there. I will give you guys another one of these example problems to have you work through on your own next time, and then we'll finish up the chapter. If you have any questions, stay around. Otherwise, enjoy the rest of your day. It's nice having y'all here. Seeing some of your faces. Brittany, you look pretty. I don't know if that's a new lipstick, but I like it. Yeah, enjoy your day.